Space travel is a long-cherished dream of our human race. We have done much preparation for this goal. Some of the concepts to make interplanetary travel possible include the creation of special spatial regions called wormholes that can cut astronomical distances between planets, transcending the limits of the third dimension. Hello everyone! Welcome to this channel. American astrophysicists are proud that their cutting-edge research is an important key to unlocking the concept of hyperspace. The theory of hyperspace will greatly help us in the future to play with beautiful aliens in faraway places. We will now tell you more about these studies. Two celestial objects and 4 dimensions. As you know, the brighter and larger a star is, the faster it burns, and it burns out in a supernova explosion. An exploding star transforms itself into a black hole or pulsar. What is a pulsar? Imagine an incredibly heavy matchbox that weighs several million tons per box. And now imagine those matchboxes piled up in a pile the size of New York or Shanghai. This would be just like a pulsar the size of an asteroid and as massive as the Sun. Furthermore, pulsars emit radio waves from both poles. Each pulsar has a strong magnetic field and also rotates very fast. The observation of a dual system consisting of a black hole and a pulsar revolving around it allows scientists to investigate the 4th dimension of space. The importance of the existence of the 4th dimension has been said at length. This is not only because, when going to another planet, the flight distance in space is normally too long. But there are a lot of questions about the conventional space system alone, which speaks in 3 dimensions. For example, there are 4 basic interactions in space: the strong force, the weak force, the electromagnetic force, and gravity. Which do you think is the weakest? No, you missed the point. It is not the action of the weak force. The weakest of the 3 is gravity. But why do we perceive gravity, which is supposed to be the weakest, as the strongest? Furthermore, each of the 4 interactions requires a special particle to transmit it. The particle that transmits the strong force is the gluon. The weak force is a few particles called bosons, and the electromagnetic force is transmitted by photons. And it is gravitons that transmit gravity. But no one has ever seen them. Where is it? According to calculations, there should be a lot of antimatter in the universe, but who lost it? The leafy universe. In response to this problem, a concept called string theory was born among researchers. This is a theory that is very difficult to understand without a wide range of perception, and under this theory, the entire universe is penetrated by invisible strings. Under this theory, there are 9 dimensions of space, with 3 major dimensions and 6 more added from there. Such dimensions exist in the microscopic world. Within the space we know, the size is Planck size, which is the smallest size that mankind can observe. In comparison with the Planck size, even the smallest electron is about the size of a soccer ball compared to the Earth. To explore such a small chunk of space would require about 1,000 Large Hadron Colliders. It is easy to guess that this theory does not suit us. First, this theory does nothing to help us reach neighbouring galaxies in search of beautiful views of exotic planets. Second, it would require building 999 new Large Hadron Colliders to confirm it. It takes that much energy to get into Planck's world. In response to this problem, scientists developed the concept of the Randall-Sundrum model as an alternative to string theory. According to this concept, the universe can be represented as a vague leaf. That leaf has 2 faces, each of which is called a brain. On one of these brainas, we exist, and this is where all the elementary particles are found. On the other side are gravitons. The interaction of the gravitons, gravity, is strong enough to affect our side, and perhaps other particles were pushed to our side by the gravitons. Here's another theory that makes our head hurt: the radius of curvature, L. If we think of the universe as a sheet of paper, the radius of curvature, L, represents the corner of the paper or the angle created by two brains. If physicists could somehow investigate it, they would be able to solve many mysteries. The first of these is, does the opposite brain really exist? And how does space act under the conditions of that opposite brain? Perhaps it could be very curved. That is, theoretically, this could cut the distance between the planets. But, of course, you have to get there first. Until we encounter the other side of the world. There remains the problem of first finding a way to observe the opposite world. Then, perhaps a black hole and a pulsar will help us solve this problem. Let us now return to the dual system of unburned supernovae we discussed at the beginning of the video. It is very convenient that a black hole and a pulsar, neutron star, can be imagined as two lumps that do not exchange matter with each other, and that their volume is very small compared to their mass. Black holes are known to evaporate. This is called Hawking radiation. The spontaneous loss of energy in the form of gravitational waves is incorporated into this process. As a black hole evaporates, the orbital radius of the pulsar rotating around it increases, and its rotational speed decreases. This phenomenon is caused by the decrease in the black hole's mass, i.e., it no longer attracts objects in its orbit so strongly. On the other hand, under these conditions, the pulsar emits gravitational waves and is conversely attracted to the black hole. This means that something like a lover's quarrel between a couple is taking place. The black hole's Hawking radiation is trying to divide the system, and the pulsar's gravitational waves are conversely trying to bring the system together. The difference between these two forces helps us find the radius of curvature, L. There are not many systems consisting of pulsars and black holes, and so far scientists do not have sensitive enough instruments to measure the gravitational emission. At present, we have to be content with theoretical calculations and indirect observations, but that is still better than nothing. Let us suppose, for example, that we have a black hole with about 3 times the mass of the Sun and a pulsar with half the mass. At this mass, the rotational period of the pulsar orbiting the black hole increases by 0.5 seconds per year, because the black hole is disappearing due to Hawking radiation. On the other hand, due to the gravitational attraction of the pulsar to the black hole, the rotational period conversely decreases by about 1/10 of a millisecond per year. These data are not hypothetical, but are obtained by physical observations of the actual reality of a neutron star system. Substituting these data into the formula gives the magnitude of the curvature L of 10 micrometers. It will be 10 to 20 years from now before we will have equipment that is accurate enough to measure this system. We only need to explore the system of black holes and pulsars with the necessary parameters for calculation and observation. Then we will finally understand where to look for the entrance to the 4th dimension. That's all for today, ladies and gentlemen. Thank you for watching. The brain on the other side is not only a valuable source of knowledge for us, but also a key to paving the way to faraway stars. We are one step closer to creating a wormhole. Also, if gravitons really exist on another brain, studying them will allow us to even manipulate gravity, which would be another great advance in science. There is still a mountain of work to be done, but great discoveries always start here. Let's work hard together. See you soon then. Bye bye.